We will go to today's lecture. Which is our next chapter. Chapter 6, Concurrent Models of Computation. As we can see in the previous module, we have actually seen how to compose the various components of a cyber physical system. We saw some basic composition techniques like cascade composition, side-by-side composition. In this module, we will be looking at concurrent models of computation. If you want to understand how to compose various models, the individual components, in order to build a model, we have to understand the various individual components. We have to also understand the interaction between the various components. This is the point that we are going to focus on in this particular lecture. We have seen the various compositions of the components. We specifically design the components as finite state machines. There are many possible interpretations for the interaction between the components. We will see some examples. The prime important aspect here we need to consider is, what is the meaning of a composition? What is the semantics? The meaning of a composition is referred to as semantics. Here we actually focus on the semantics of concurrent composition. As we know, the cyber physical systems actually work and perform their activities in a real world which is actually concurrent or event based. There are several activities or processes that need to run concurrently, and the cyber physical system needs to put together all these components and has to define a semantics for this particular concurrent composition. What do we mean by concurrent composition? Basically, the term refers to running together. There are different parts of the system and they conceptually operate at the same time. As we know, if there are two entities that actually operate at the exactly same time, we see that these can lead to chaos because different activities run at exactly the same time in an unpredictable fashion. Here we need to understand what are the dependencies between those activities and how they can be ordered. We have to impose this particular order, and it is that which is the semantics is going to help us to understand. Here we introduce a concept which we call the model of computation, or the MOC. We actually impose certain rules, and these rules can be classified into three or split into three. The first rule specifies what is a component or what constitutes a component. Here we can, as I mentioned in the previous slide, in the previous module we have seen that a component is actually a finite state machine. The second set specifies what are the mechanisms of this concurrency. So we have several mechanisms for concurrency. The second set, or the second part in the model of computation, must explicitly specify what are these mechanisms. The third set specifies what are the communication mechanisms between these different components. What is a component? A component is an actor with a ports and set of execution actions. This we have seen over the course when we discussed the continuous systems and the discrete systems. We spoke about actors. We also spoke about the various ports that these actors have, and the ports actually give facility to these actors to receive inputs and to produce outputs, and when it takes inputs, it executes certain actions to produce an output. So this simplified model of actor will be used in this while discussing the model of computation. Now, how the actor reacts to the inputs and produces the outputs and changes its state. Here, apart from reacting to the input and producing the output, has to change the state. So this is where the finite state machine comes in, and we have seen the finite state machine and the extended finite state machine. Now the ports are interconnected to provide for communication between the actors. We know that there is a type check that needs to be performed when we actually provide output from a particular port of a certain actor, and that is provided as input to another actor to a particular port. So the type must match between these two ports, and this is what we refer to as type checking. Now there can be execution actions that are invoked by the environment of the actor to cause the actor to perform its function. Now here the environment is actually providing the input. So in a finite state machine, we know that one particular action is provided that produces a reaction. What is the focus of this chapter? Here we introduce a few possible concurrency and communication mechanisms. So when we say concurrency and communication mechanisms, it reminds us of the concurrency and communication mechanisms that we have learned in the operating systems. So here we also have similar concurrency mechanisms, but the difference is that we are talking about real-time systems that operate in a real world. Now these concurrency mechanisms must govern the interactions between such actors. Now we need to discuss the common structure of the model that applies to different model of computations. As we know, there are different approaches to building different models of computations, and we will see few of those variants of these MOCs. Now let us look at the structure of models. So we are trying to make explicit some of the important aspects of certain component, or specifically an actor. Now the interactions between the actors specify the communication paths. The communication path is, we specify a communication as a signal which consists of one or more communication events. So a signal does not specify it carries only a single set of information or a single data item, but rather it actually focuses on carrying a certain set of events, but at a particular point of time we call this as a signal. Now a signal which we have seen in the form of a function, we have seen for a discrete signal can be specified as S, and which maps from the real world to the set of signals which we call Vs, or the valuations and of the particular port, including a situation when there are no events or no signals, which specifies a null set or an absent set. Now we set the set of values Vs, we call it as the type of the signal S, and it is non-absent, else it is absent. Now when we come to a continuous time signal, we always have some sort of signal that is present. There is no absent concept here, or there is no there is no point of time when the signal is absent. Always there is some sort of signal that is present, and we map from the real numbers to the set of the type of the signals. Now here we have an uncountably infinite set of values for each particular time in the time domain. But if you want to specify it to make it more to specify it as a sequence of values, we can specify the ream from the set of natural numbers to the different types of signals. Now, as I mentioned before, there needs to be a type check when a signal is moving from one particular port of a particular actor to another input port of another particular actor. For example, a particular port Y, okay, of actor A to another particular port of actor B. So if this is a port and this is another port, if we have two actors A and B, and we can see that this is moving from a particular port output port Y, and this is moving to an input port X. So this valuations should be such that Vy should be a subset of Vx. So this what we refer to as type check. Now let us look at a diagram. Example 6.1. We will do an exercise after this. Here we can see there are sort of actors that are defined, and here we can see there are two types of composition. One is a side-by-side composition, and there is a feedback system also. Now this diagram, if you can see, it takes us through 4 stages A, B, C and D, where we are actually simplifying the system. So in the first stage we have 3 actors A, B and C. Here we have combined the 3 actors and we have actually rearranged them to form a side-by-side composition. So here in the case of A, there is no side-by-side composition apart from A and B and C and B. There is a feedback composition from B to A. Here we actually, when we move to figure B, we have simplified the system and we have actually rearranged the actors A, B and C in such a manner that the actors form a side-by-side composition, and this side-by-side composition can be is depicted by the yellow rounded rectangle, which we can see here. Now this box itself is an actor F, which we can see here, and here we have generalized the actors A, B and C to an actor F, and we have represented the ports of the various actors. For example, the port of actor A, which is P1, and the port of actor B, which is P2 and P3, have been generalized to be the ports of actor F. For example, the input ports of actor A, which are P1, and the input ports of actor B, which are P2 and P3. So in total, if you see figure A, there are 3 ports, P1, P2 and P3, which are the 3 input ports, and the output ports are P4, P5 and P6. In actor F, we have actually generalized this, and we have actually created 3 input ports and 3 output ports for this actor F. So the input is 3 tuple and the output is also 3 tuple. So this we will see. Now we can further generalize this actor F into a single actor, where we are going to specify the set S is equal to S1, S2 and S3. Now the 6.1D is a feedback system. We can use the same procedure that we have seen here to build interconnection of actors and structure it as a similar feedback system. So let's look at how we have done this. Here we can see that in the actors that we have seen, the signal is present if T is a multiple of P, and it is absent otherwise. So here we are considering the actor as a pure signal, and the signal is S, and the signal is present if it is the signal is present if it is signal is present, if it is a multiple of p, and otherwise it's absent. So such a signal is called a clock signal, and it has as a clock signal with a period p. It occurs, communication event occurs every p time units. So this is an example that we that is just used to mention, that is used to make clear the signal S, and this signal S can be similarly seen to be a signal S of this final actor F that we have used. So here we can see that we can represent an actor in a more simplified manner. Let's look at an example. That is an example of that is the exercise that we have in the textbook. So the question is, show how each of the following actor models can be transformed into a feedback system by using a reorganization similar to that in figure 6.1b. So the actors should be aggregated into a single side-by-side composite actor. So let's see how we can do this, and we will try to do this on paper, and we will see how we can actually simplify this. So starting with the first 1A, we see that we have two actors, F1 which has a port P1 and F2 which has a port P2. Now how can we convert this into a feedback system? So let's rearrange these actors in this fashion. The output coming from F1 will be given as a feedback to the input of F2. Now we can generalize this by drawing a single actor F with the same input given as output. So here I will just specify this is P1 and this is P2, and this I can write as P. Or since there is only one, I can write it as P1 and P2. So here we have transformed this. This is 1, the 2 and the third. So this is quite straightforward. Kindly excuse the quality of the drawings because I'm using a laptop webcam and it doesn't give me that much quality, but I hope that you can make it out from this figure. Now let's go to the second exercise. This is A. Let's go to B and see how we can draw it. So in B, the question is, we have three actors, which is also quite straightforward. F1, F2 and F3. So this will be P1, P2, P3 and P4. Now how can we draw? We can use the same method that we used previously. Just draw the three actors. So first we need to find out which is the actor that produces the output. So we will draw F1 here, and this will go to F2 and F2 will go to F3. So F1, it will go to F2, so this will become F2, and the output from F2 will go to F3. So you can draw it in another fashion also. We can put F3 on top and F2 on bottom, it doesn't matter, but anyway the final output again will be same, but just to write down the ports this will be the output port P1. Now as we can see, there are two output ports here, P1 and P3, and there are two input ports, P2 and P4. So this will be P2 and this will be P4. Now if you combine this actor into a single actor F, we can draw this as P and P. So this will be drawn in such a manner. This will be going here, and this will be P1, and this will be P4, and this will be P3, and this will be P2. So here you can see that there are two ports, P1, output ports P1 and P3, and the input ports are P2 and P4. Now let's try to generalize this actor now. So we will use, if we have the signals, as I said earlier, we can write S. Let's say we have the signals S equal to S1, S2, and we can write this as will be S1 and this will be S2. Okay, so I'll just draw this as S2. S1 and S2. Now I can combine this actor into a single actor as earlier by drawing F and writing this as input and output port, and this will be denoted by S. So this will be the final output that we will get for the actor. Okay. Now let's move to the next diagram, which is C. So this is slightly more different because it has concurrent as well as side by side composition. So I will just draw this slightly bigger. I will just redraw this. Two actors at the bottom, and there is one actor in the middle. Kindly excuse my style of drawing. I just managed to show this to you, but so that I can work on the exercises. I thought I would do it on hand, so you can just try it out. Hope you can make out my handwriting. The webcam is also slightly at a different orientation. So this is the diagram. So here, as you can see, there are three actors, F1, F2 and F3. P1, P5, P3 are the output ports. The input ports are P2, P4 and P6. How can we draw this? So let's again follow the same fashion of putting it one by one below. We will label it later. For the time being, let's try to draw one by one. So there is no specific rule, but I will just put F1. I will put one actor on the bottom, which is F1, and I will draw the F3 here. So we will just go all the way here and come back here. This is the P5 and this is P6. Now I have one more connection from P1 to P2, which is F2. So I will follow that, which is P1, and I will go here, and this will be as input as P2. Now there is one more connection which is called P3 to P4 from F2 to F3. So again this will be coming from F2 P3, and this will be going to F3 as P4. So here I have three P1, P3 and P5 the output ports, and P2, P4 and P6. So I will just mark this with a different color. So these are the output ports, and these are the input ports. So I don't know whether you can make out the color, but just mark these ports. Now the question is, how do I combine these two? So it's the same strategy that we have used earlier. I will just draw this actor F, and here I will have 2 3 in output ports and 3 input ports. So this will be P5, so it doesn't matter which one you use. So this will be P3 to this thing, this will go here, and this will go all the way here. So this will be you can just write this as any order you want, but P3, P1, P5, P2, P4 and P6. So this is the actor, and I will just represent this actor as a single F. So I will just mark this signals as S1, S2 and S3, and here I will just write down this set which is S is equal to S1, S2, S3. Now I will just represent this set S as a signal from here to here. So this will be representing S. So this is my F. So this is how you can work out example exercise 1. Now let's go back to our discussion. So this is the set of equations that you can see. So let's come to the discussion. So the strategy that we used here is, if we rearrange the actors, then the actors form a side-by-side composition which is indicated by the box with the rounded corners. Now we will get an actor F whose input is 3 tuples. There are 3 signals, and it is a set of 3 signals, and the output will be a set of 3 signals. So this is the example that we saw earlier, which was this example, and it also applies to this example that we just saw right now. It applies to the same example also. Now as we can see, if you put S equal S1, S2, S3, the actor can be depicted as the figure 6.1d, and it hides all the model complexities of the model. So this is one important thing that we need to actually look for, which says that the actor can be depicted and the complexity of the model can be hidden. Now how do we represent an actor as a system of equations, or we represent actor networks as system of equations? Now as you can see, the actor network that we just saw, we need to represent it as a system of equations. Now we can see that any actor can be represented as a function which maps the input to the output using a certain function. So we know that we have a similar kind of function which we call the update function for a finite state machine, which actually if we give it the set of inputs, the current state, it gives us the output and the next state. So similarly, when we generalize that, we can say that an actor can be represented as a function which acts on the input and produces the output. So here we can see that in the figure 6.1a, we can represent the actor A as S2 is equal to A of S1. If you look here, we can see that the actor here is producing the signal S2. It can be represented as an input function of a signal S1. So S2 is equal to A of S1. Similarly, B can be written as the input is of input is S2 and S3, so the output S1 will be equal to B of S2 S3. Similarly, C doesn't have any input, but it produces a constant output which is S3. So let's look at how we can model this intricacies. Here we can see that actor A, S2 is equal to A of S1, actor B, as I said, S1 is equal to B of S2 S3. The function C doesn't have any input and it's a constant function. Note that it is a constant function and produces the same output for every input, that is the C of null set will be equal to S3. Now this is a set of functions that we have. So let's just digest this set of functions, and once we have this set of functions, we actually give f of S1 S2 S3 it will be equal to B of S2 S3, A of S1 and C of phi. So this is very important. Here we have mapped the three signals to their corresponding functions, which is B, A and C. Now moving forward, we have seen this example. Let's come to the next topic, which is the synchronous reactive models. Okay. So I think we will directly move to the synchronous reactive models. We want to have a synchronous composition of state machines. So when we say synchronous, we usually refer to as the presence of a clock, and when the clock trigger occurs, all the actors react during that particular time period or the particular clock instant. So how do we actually build this feedback compositions as synchronous composition of state machines? So let's have a look. So for this we need to understand the concept which is called fixed point. So let's move to understanding what exactly is a fixed point. So before that, let's understand a few terms which is related to the fixed point. So one is called determinacy. So what is meant by determinacy? A state machine is said to be deterministic if for each state there is at most one transition enabled by each input value. So the term itself, determinacy, is basically talking about the deterministic nature. Okay, it's talking about whether it's a deterministic state machine or it's a non-deterministic state machine. So when it's a deterministic state machine, there is one transition that is enabled by each input value. Okay, the formal definition of such a FSM ensures that it is deterministic. For example, this update is a function basically. So update is a function and it's not a one-to-many kind of mapping. Okay, so update is a function. So when you say it's a function, it maps a set of input values to a constant set of input values. So in the domain and the range, there is a unique value in the domain for each particular range, for each particular value in the range of the particular function. Now the state machine will be deterministic only if the guards leaving each state are non-overlapping. So if there are a set of guards that we use for each particular state, they will be non-overlapping, meaning that they are deterministic. What is a determinate actor? Now a determinate actor is slightly different. A deterministic state machine is determinate that given the same inputs, it will always produce the same outputs. So this is very important. This concept, it's very, very important that you need to understand here, is that a deterministic state machine is actually it produces same outputs for the same set of inputs. Now we need to understand that if a state machine is deterministic, it doesn't mean that it is a determinate. Okay, so not every determinate state machine is deterministic. So being a deterministic state machine is different from being a determinate state machine. Now what is the importance of being determinate? This is what we need to answer. So this is what we need to answer. For this we need to understand the concept of a fixed point. So now let's directly go to the fixed point semantics. Now if the actors are determinate, if an actor is determinate, each actor is a function that maps the input signals to the output signals. So the semantics of such a model will be S equal to f of s, where s equal to s1, s2, s3. Now this might seem simple, but the complexity of this lies in the definition of f and the structure of both the domain of f and the range of f. That is, what is the inputs and what are the outputs. So what is the structure of the inputs and what are the structure of the outputs? It depends on that, and that is where the complexity of this function f lies. So if you see that given any function f which maps from set x to another set of inputs, it maps from set x to set x, the set of inputs it belongs to set x, to another set of outputs that belong to set x. If you have a particular value of x, which is an element of capital X, such that f of x is equal to x, that is, if we give the input we receive the same output, then the semantics of a determinate actor network, this particular point, this particular point or this particular value of x is called a fixed point, which is f. Now this point is called a fixed point, and that is x. The fixed point is called x. Now just have this graph that we can see here. If you look at this function y is equal to f of x, it may be any arbitrary function. Now if you fit if you just fit this function with a straight line, which is y is equal to x through the origin. Now if you look at this straight line and this function y equal to f of x, which can be any arbitrary function, maybe the sine function or it may be cos function, it may be any function, we can see that at certain points the input is equal to the output. If you look at the grid, we can see that the input is equal to the output, which are denoted by the yellow dots that have been displayed on the graph. So these are the fixed points that we just mentioned. Now these fixed points can actually be anywhere. It can occur somewhere here also, or it can occur somewhere here. It can occur in any part of the graph, in another graph, not the specific graph. It may not occur at all. There may not be any specific fixed points at all for a particular graph. There can be more than one fixed point. There may be one fixed point. Now why I am mentioning this to you is there is a specific meaning for each of this when we have no fixed points at all, when we have a single fixed point, or when we have multiple fixed points. So we will look at what this means as we progress in this lecture. So the semantics of a determinate actor network is a fixed point. This is very important, what I just wrote here. The semantics of a determinate actor is a fixed point. So if you have a determinate actor network, the semantics is a fixed point. For a determinate actor to be for actor network to be determinate, we need to have a fixed point, and that is the semantics of this particular actor network, or more specifically a determinate actor network. These are the questions that I just mentioned. How do we find this fixed point? And this is core to this model of computation, these questions. Now let's look at the synchronous reactive model of computation and how we can find the fixed point in the synchronous reactive model of computation. Okay. The execution of all actors is simultaneous and instantaneous, and it occurs at all ticks of the global clock. If the actor is determinate, then each such execution implements a function called the firing function. We already know what is a firing function. Firing function takes an input and it produces the output at the occurrence of a particular global clock. Now let's take an example. In the nth tick of a global clock, the actor A implements a particular firing function of the form. It has a type V1 and it maps to a type V1. Basically it's a discrete signal, so that the signal can be present or absent, and whenever it's present it takes values from the set V1. This is called the type of the signal, and for each particular signal, SI, VI is the type of the signal. Now if we say if SI of n at the that is value of the signal I at a particular tick of the clock, that is the nth tick of the clock, then we can see that S2 of n is equal to AN of S1 of n, which says that the value of the clock at the second tick, nth tick, the value of signal 2 S2 will be a function of AN of S1 of n. It will be a function of S1 of n. Now let's look at 6.1d and how we can rearrange that, as just told you, as a system of equations which I have already seen. Now let's consider the firing function fn for each actor f. Now in figure 6.1 we can define the execution at a single tick by a fixed point. Sn is equal to fn of Sn, where Sn is equal to S1 of n, S2 of n and S3 of n. Now we know that S1 of n is equal to Bn of S2 of n, S3 of n, and S2 of n is equal to An of S1 of n, and S3 of n is equal to Cn of phi. So this is the fixed point that we have got here. So I will just repeat this. If you have a firing function which is f of fn, for this fixed point to occur, the fixed point should be such a manner that we will get the fn of S1 of n, S2 of n, S3 of n will be equal to Sn. That is Sn will be equal to fn of Sn. So this is what we need to understand. This is the fixed point that we are talking about. Now we know that the Sn is defined as here, where the Sn is S1 of n, S2 of n, S3 of n. Now what is this S1 of n, S2 of S3 of n that we have just seen here? This is the S1, this is the S2, and this is the S3. So here the S1 of n, S2 of n, S3 of n is defined by these functions. Similarly the f. Now if we take fn as a firing function, or fn is a firing function, the fixed point can be defined as Sn is equal to fn of S of n. That means where we define fn of S of n is equal to fn of S1 of n, S2 of n, S3 of n, which is equal to that what you just saw. Defining S1 of n will be as B1 Bn S2 of n. S2 of n will be equal to A1 of S1 of n, and S3 of n will be equal to Cn of phi. So what is the conclusion? For synchronous reactive system, the semantics at each tick of the global clock is a fixed point fn, just as its execution over all ticks is a fixed point of the function f. Now it is difficult to understand this, or it may be confusing to you, especially if the fixed point concept is not clear. A fixed point concept just tells you that the actor is determinate, because the semantics of a determinate actor is a fixed point. So if an actor has a fixed point, we can say that it is determinate. So for a synchronous reactive system, when we are talking about when there is a presence of a global clock, and for each tick of the global clock we have a fixed point of the function fn. If you take overall execution of all the ticks, there exists a fixed point of the function capital F. So there is a function for a fixed, there is a fixed point for the firing function, and the fixed point for the global function f. Okay, so we will move forward and we will try to understand this. So let's move forward and look into detail at the synchronous reactive model. So we studied the synchronous composition of state machines in chapter 5, but we did not go into depth about the behavior of the feedback compositions. So we saw an example of this is an example that we have seen in the previous chapter 5, where that is the composition of state machines. This is a similar kind of construction where we actually have a side by side composition along with a cascade composition. So here we can see that there are questions that we need to answer, like which machine will react first, because we need to understand that whether the output at port the input port at A1, which it is not specified here, so let's say that the input port here is P1. So the question is whether the output occurs first or the input occurs first. So here at P1, for P1 to receive something, the output should occur first at P4. So for the output P4 to occur, first A1 and A3 should react first. So for A1 to react, we need to have output from the port P4. So these are some questions that we need to answer. So these questions can be answered only if we know what is the model of computation. Now for the with respect to the figure 6.1 that we saw earlier, the state machine, in order for it to react, we need to know its inputs at the time of reaction. This is important. But the inputs are same as outputs, so the order for it to react, we need to know its output. But we cannot know its output until after it reacts. So if we look at the exercise 1 that we have just seen, that we just did, we can see that how we can actually how this will be a problem. So we need to understand whether which of these inputs where the inputs occur first and which actor reacts first, so that we can find out the exact sequence of operation of F1, F2, F3, and finally predict what will be the output. So this is basically the important question that we need to answer. Okay. All actor networks can be viewed as feedback systems. So we have to solve this issue, because whenever we view an actor as a feedback system, we need to solve this issue. Now an SR model is a discrete system, a synchronous reactive model of computation. SR model is a discrete system where the signals are absent at all times except at the ticks of a global clock. Signals are absent at all times except at the ticks of a global clock. Conceptually, the execution of a model is a sequence of global reactions. The execution of a model is a sequence of global reactions that occur at discrete times, and at each such reaction, the reaction of all actors is simultaneous and instantaneous. So whenever the tick of a global clock occur, the all actors react instantaneously and simultaneously. They react instantaneously and simultaneously. Okay. So there are signal is absent at all the times apart from when the ticks occur of the global clock. So we can do it, or we can now proceed by giving this model of computation by using this concept called the synchronous reactive model of computation. So first we will focus on model of the feedback models that we have seen in figure 6.1d. So first we will assume, or first we will consider that F is realized as a state machine. At nth tick of the global clock, we have to find the value of the signal S, so that it is both a valid input and a valid output of the state machine given its current state. So we need to find the value of the signal S. So it is both a valid input and a valid output of the state machine given its current state. So let's say that let S denote the value of the signal S at the nth reaction. Now our goal is to determine that at each tick of the global clock the value of S of n. So whenever we know that we have set of valid inputs and valid outputs, and the value of S, signal S at a particular nth reaction, okay, we need to find out what is the value of S of n. Now let's take an example 6.2 from the textbook. So this is a similar example just shown in S6.2, and this is simpler than 6.1d because signal S is a pure signal rather than aggregation of 3 signals. Now there is only one signal here, and it's a feedback system. Now we have two states, a state machine with two states, S1 and S2, and if A is in state S1 when the reaction occurs, then the only possible value of Sn is to be absent, because the reaction must take one of the transitions out of S1 and both of these transitions emit absent. Here we can see that if you take this and this, there are two reactions from the state machine, and both cases the output is absent. So the possible value of at any instant of the global tick, the output will be absent when the system is in state S1, since both transitions emit absent. Moreover, once we know that Sn is absent, we know that the input port X has value absent, so we can determine that A will transition to state S2. So whenever we know that it has taken this transition, the output will always be absent, but it will transition to state S2. Let's analyze this further. Now if we look at this and if we simplify the state machine, just like we simplified the figure in 6.1 and we made it like in 6. Just the exercise that we have done, we have simplified this from here to here. Let's see how we can simplify the state machine here. So in the state machine we can see that we have simplified the state machine, saying that whenever there is an input, so this whenever at the global tick of the clock, we can see that a transition will definitely occur to S2. Okay, so the transition will definitely occur to S2 and the output will be absent. Okay, so now what about the second state? In the second state S2, we can see that state S2 we can see that whenever there is an input or whenever there is no input, the output produced will always be Y. Okay, and whenever there is an input, the transition will be taken to S1. Okay, so when we can simplify this, we can see that whenever there is an input, that is irrespective of whether there is an input or output, the output is absent in the case of transition from S1 to S2, and irrespective of the presence of input, the S2 will produce an output Y and it will transition to S1. Okay, so the transition from S1 to S2 will always happen. So in the cases when there is no input, the transition will happen from S1 to S2, and whenever there is an input, the transition will occur from S1 to S2 to S1. So whenever there is so at each global tick of the global clock, the transitions will occur, but the outputs will always be absent and present. So S will alternate between absent and present. S alternates between absent and present. The semantics of machine A in the feedback model is therefore given by figure 6.1. So this is the equivalent machine that we have derived, state machine of this particular state machine that we see here. So this is the semantics of this state machine. So this is how we have derived this semantics. Okay, so this fixed point that we have just learned is actually used to go into deep into understanding. Now this is a simple state machine that we have seen here, because there is just one input and one output, so it's very simple. But if there are multiple inputs and multiple outputs, there may be different possibilities, that different reactions that may occur at each state, and different update functions also, and the signals may not be pure also. So in that case we need to find out the fixed points, and then we can determine the semantics. So these are some things that we can say about this feedback systems. So most of the things have been already mentioned. So just talk about this third point. Given a deterministic state machine in a feedback model like that of this figure S6.2 that we have seen just now, the state machine that we just saw here, figure 6.2. So each state I, we can define a function AI that maps input values to the output values. So here in this case we are mapping from present absent to present absent. Now for the example in figure 6.2, the machine is in state S1, then S1 of x is equal to absent for all x is element of present or absent. So for all present or absent, the output will be absent in state S1. This is what we can deduce from the figure 6.2 state machine. The function AI, as we already know, is called the firing function for the particular state I. Now given a firing function, to find the value of Sn at the nth reaction, we simply need to find the value of S of n such that S of n is equal to AI of S of n. Is it clear? So here we need to find out the value of a S1 of x. So here a S1 of x is always absent. Whenever it's in the state S1, the firing function produces an output absent under all circumstances, whether the input is present or not. So if you can find a value S of n where the output is equal to the input for the particular firing function AI for the state I, then S of n can be called a fixed point. And the signal S need not be a single signal, can be an aggregation of signals. So that's why we need to simplify this, as we have just simplified in this diagram here. We have simplified this. Here we have three signals S1, S2 and S3, which we have simplified to a single signal S. Here we need to find the fixed point. Okay, we need to find the fixed point in terms of these three signals. Now let's talk about well-formed and ill-formed models. Okay. There are two potential problems that may occur when we seek a fixed point. First, there may be no fixed point, as I told you. There may be more than one fixed point, and in either case occurs in a reachable state, we say that this system is ill-formed. Okay, so when there is no fixed point and when there is more than one fixed point, we say that the system is ill-formed. Now otherwise the system will be well-formed. Now let's take an example 6.4. Now consider the machine B as shown in figure 6.4. In the state S1, we get the unique fixed point Sn is equal to absent. In the state S1, we get the unique fixed point Sn is equal to absent. In state S2, however, there is no fixed point. So let's look at the state S1 first. So I am not sure whether this figure is visible to you. If you look at the state S1, here we have two inputs. We have one input and one output, both of which are pure. In state S1, we see that we get the unique fixed point Sn is equal to absent. In state S1, we get the unique fixed point Sn is equal to absent. So here we see that whenever the input is absent, the output is also absent. But in the state S2, there is nothing of this sort. In state S2, we see that there is no fixed point. If you attempt to choose Sn is equal to present, then the machine will transition to S1. If you attempt to choose Sn is equal to present, if you attempt to choose Sn is equal to present, then the machine will transition to S1 and its output will be absent. But the output has to be same as the input, and the input is present, so we get a contradiction. Similarly, we get a contradiction if you choose Sn equal to absent. So here we can see that in state S1 we get a unique fixed point which is absent, but in a state S2 there is no fixed point. So what can we say about this model is the question. Since the state S2 is reachable, this feedback model is ill-formed. So in one state there is no fixed point, means that we should have a fixed point in both S1 and S2, then we can say that the model is well formed. What did we say here? If there may be no fixed point and there may be more than one fixed point. If there is no fixed point, it is okay, it is well formed. But if there is if there is no fixed point, or if there is more than one fixed point, it will be ill formed. But otherwise it will be well formed. So we can say that the system is ill formed because it has no fixed point in state S2. If it had a fixed point in state S2, it would have been well formed. Let's look at another example. 6.5. In this example 6.5, we can see that there is a fixed point in state S1. That is, when the input is present, the output is also present. What about in state S2? Yes, when there is the input is present, the output is also present. But in state S2, we can see that even when the input is absent, the output is present. Okay, so here we can see that in state S1, in state S1 there are two fixed point. That is, when the input is present, the output is present, and when the input is absent, the output is absent. While in S2 there is one fixed point which says that when the input is present, the output is present. So here S2 state has one fixed point, while S1 state has two fixed points, which means that when the number of fixed points is more than one, the feedback model is ill-formed. Now, if we can look at different alternative semantics. That is, if in a reachable state there is more than one fixed point, we can declare this machine to be ill-formed. But rather than rejecting the model, we can say that it would be non-deterministic. When we say that the state system is non-deterministic, we can say that we can divide that particular state into a non-deterministic state, and then we can say it will be a valid semantics. But the problem is that the disadvantage is that the composition of a deterministic state machine is not assured to be being deterministic. So if you take two deterministic state machines, and if you compose those, we cannot say that the resulting state machine is also deterministic. So if we say that the alternative semantics would be to assume that the state machine is non-deterministic, we can say that it will be a valid semantics, but the disadvantage is the composition will not result in a deterministic state machine, which we have already discussed in previous example. So determinism would not be a compositional property, hence we prefer to reject such models. Now we will look at how we can construct a fixed point, and we will just quickly go through the procedure of constructing a fixed point. One way is exhaustive search. One way to find a fixed point of type ES of the signal S or the signals is an aggregate of an aggregate of F is finite. Then if exactly one fixed point is found, then the model is well formed. The exhaustive search is expensive and impossible if the types are not finite. So if the types are not finite, then the exhaustive search is difficult. So if it is finite, the signals, if we take certain aggregate of signals, if they're finite, types are finite, then we can use exhaustive search. Again, it will be expensive, but if it is infinite, it is impossible. So we need a systematic procedure. So what is a systematic procedure? This is how we can construct a fixed point. So for each reachable state I, we start with S of n unknown. So determine as much as you can about Fi of S of n, where Fi is a firing function in state I. Note that in this step you should only use the firing function which is given by state machine. You should not use knowledge on how the state machine is connected on the outside. We should only use the knowledge about the firing function. Now second, repeat step 2, which is I have not marked the steps as 1 and 2. I will just mark them. Somehow I missed those. So this will be 1, this will be 2, this will be 3, this will be 4. So we have to repeat the step 2 until all values in S of n become known, whether they are present and what are the values, or until no more progress can be made. If unknown values remain, then reject the model. So it's very simple. We start with S of n unknown. That's a particular tick of a global clock. What is the value of S? We have to find out what as much as possible about the firing function Fi. We should only use knowledge about the firing function, not how the state machine is connected to the outside. We should not think about like what are the inputs that may come, or what are the impossible inputs, etc. Now when we repeat the step 2 until all values in S of n become known, whether they are present or absent, we need to find out all the values of S of n, whether they are present, what are the values are, and until no more progress can be made, we do that. We keep on repeating it. When unknown values remain, we reject the model. Now let's look at how we can apply this for an example 6.6. For this particular example, now if you consider the state machine D, in state S1 if the input is unknown, we cannot immediately tell what the output will be. Is it correct? State S1, we say that if x is equal to 0, there are two values, a 0 and 1. 0 doesn't mean that it's absent. 0 means that there is an input that is present, which is value of 0. So when the input is 0, the output is 1. But when there is no input, that is, there is no input 0 or 1, the output is absent. So when the input is unknown, we cannot tell what is the output is. So if the input is absent, we don't know what will happen. When the input is absent, we know that it will transition to S2, but if the input is 1, what will happen? It is not clear. Now we have to all try possible values for the input to determine that in fact S of n is absent for all n. So we can say that whenever the input is 1, the output also again has to be absent, just like when there is no input at all. So there are two cases here: when the input is 1 and when the input is absent, the output will be absent. Now if you look at state S2, we can see that we can immediately determine the machine must produce an output. Somehow it has to produce an output. Okay. If you look at state S2, we can see that whenever the input is absent, the output is also absent. So there exists a fixed point in state S2. But in state S1, there exists a fixed point here. But the problem is, whenever the input is 1, the output is also absent. So we can see that there is a confusion, or we cannot immediately say what the output will be if the input is unknown. We have to try all possible values for the input to determine that S of n is absent for all n. Now let's look at what is a constructive state machine. A constructive state machine is one in which the procedure works in all reachable states. It's whenever the procedure works for all. In this case, the procedure does not work in this example 6.6, but whenever the procedure works, we can say that state machine is constructive. So this state machine is not constructive, although we can say that it has two fixed points both in S1 and S2, and in that case it is well formed, but it is not constructive because we have doubt about what will happen when the input is 1. So for non-constructive state machine, we are forced to do exhaustive search or invent some other elaborative solution techniques. Since exhaustive search is too expensive for practical use, many SR languages and modeling tools reject this non-constructive model. So non-constructive models are rejected. Now how exactly can we determine the outputs if the inputs are not all known? So we are going to look at something which is called a must-may analysis of the model. So examining the machine, we can determine what must be true of the outputs and what may be true of the outputs. So what must be true of the outputs and what may be. So what we know and what we have some doubt about. So we divide it into two. What we know and what we have doubt about are the two things we refer to as the must-may analysis. So let's look at example 6.7 and then we will conclude this part. So if you look at the model 6.2, in state S1, we can immediately determine that the machine may not produce an output. Yes, it is clear that the machine may not immediately produce an output all the times. Therefore, we can immediately conclude that the output is absent even though the input is unknown. So when the input is unknown, we can conclude that the output is absent. Okay. In figure 6.2. Sorry, I just go back to figure 6.2. This is figure 6.2, so I'll just erase this annotations. So in the figure 6.2, I'm sorry I did not put this figure in that example, so I will just maybe just look at this figure in the textbook. You can just refer this figure in the textbook so that we need not jump forth back and forth again. So let's look at this figure 6.2 in the textbook. So in this figure 6.2, we say that it is constructive because we can see that the actually what happens here is like we can immediately determine the machine may not produce an output at all. There is no output at all. So we can conclude the output is absent. That is clear. So even though the input is unknown, we do not know what is the input, but we are sure of the output. This is the must. Now once we have determined that the output is absent, we know that the input is also absent. hence the procedure concludes. So whenever we say the output is absent and it has transition to state S2, we know that the input is also absent. Similarly, in state S2, we can say that the machine must produce an output, so that we can immediately conclude that the output is present. So here we can say this is a constructive state machine because we are sure of certain things, and these things that we are sure of in state S1, that the output is always absent, and state S2 the output is always present. And in state S1 we can further say that whenever the output is absent, the input is also absent, and the state reacts and it moves to state S2. So this is what we know about the example 6.2, figure 6.2. Now we can apply this procedure to an arbitrary model structure. Let's see how we can apply this to an arbitrary model structure. First we begin by labeling all the signals unknown. Okay, all the signals are unknown. Now we examine each actor to determine whatever can be determined about the various we examine each actor to determine whatever can be determined about the outputs given its initial state. We repeat this until no further progress can be made, at which point either all signals become known or we reject the model as either ill-formed or non-constructive. Once we know all signals and all actors can make transitions, and we repeat the procedure in the new state for the next reaction. It's correct. So we start by begin by labeling the all signals as unknown. We examine each actor to determine whatever can be determined about the outputs given the initial state. So we have given the initial state, and we determine whatever about the outputs, just like we determined before that the output will be absent in all cases for figure 6.2. Now we repeat this process for the other inputs also, and we repeat this until no further progress can be made. So at this point we know everything about all the signals, or we do not know certain things, or we are not sure about certain things. In this case we reject the model as either ill-formed or non-constructive. Once we know all signals, all actors can make state transitions, and we repeat the procedure in the new state for each new reaction. So there are multiple, for the remaining number of states, since we know we know information, or we have information about all the signals, the actors will make this transition to the different states, and at each particular state we can repeat the same procedure, steps 1, 2, 3. So at step 3 we reject the model as either ill-formed or non-constructive. So whenever we know something we are not sure about, we can simply validate the model as being non-constructive or ill-formed. Of course, being informed is very easy if you just look at the fixed point. Now, when encountering a non-deterministic choice, we make an arbitrary choice. Now, when we come to a non-deterministic choice, we make an arbitrary choice. That is, maybe this is the same output that is being produced for two different inputs. Okay, or if you take two transitions for the same input. So that is a non-deterministic choice. So in that case, what do? We make an arbitrary choice. If the result leads to a failure of the procedure to find a fixed point, then we could either reject the model. So if we use this method and it fails to the method fails, or procedure fails to find a fixed point, we reject the model. And not all choices lead to a well-formed or a constructive model. Or reject the choice and try again. We reject the choice that we have made, the non-deterministic choice, arbitrary choice that we have made for the non-deterministic character, a non-deterministic state. We made arbitrary choice. If that choice is wrong, we make another choice and try again. So this is the various options that we can try. In the SR model of computation, the actors react simultaneously and instantaneously, at least conceptually. Achieving this with realistic computation requires very tight coordination of the computation, because they react simultaneously and instantaneously, at least in the concept level. We consider next a family of models which is called as a data flow models of computation that require less coordination. So that concludes this lecture. In the next lecture we will look at data flow models of computation. Thank you for listening.